Hello everyone, welcome again to my class. This is lecture number 7 and in this lecture we will learn about matrix method, which we have started already in the last class. We will dive deep into this method and see how to model refraction in matrix, or how to write refraction in a 2 by 2 matrix. Yeah, as you know, this is module 2 and we are learning matrix method in paraxial optics. Okay, in the last class we learned how to write the matrix for a translation. Yeah, in translation, if we have 2 points, then we replace this translation with a 2 by 2 matrix. Now we will try to formulate a matrix for refraction. This matrix is called refraction matrix. Okay. Now suppose we have a spherical boundary or a spherical refracting surface which is separating two media of refractive index n1 and refractive index n2, and suppose an object is placed at point A and the light which is emanating, which is coming from point A, it falls at point P on the refracting surface, and after getting refracted it goes to point B. This is the after refraction, the direction of propagation of the ray is PB. Yeah. Now, since the refracting surface is spherical, we can extend it into a circle and this circle has a center C. Now, if we want to draw a perpendicular at point P, we will have to join point P with C, and therefore, NC will represent perpendicular at point P. Once perpendicular is known, we can easily calculate the inclination of the incident ray with the perpendicular, which is represented by theta 1 in this diagram, and the angle of refraction as is shown in the figure is theta 2. Yeah. Now, we will apply Snell's law here, and the Snell's law says that n1 sin theta 1 is equal to n2 sin theta 2. Okay. Now, since we are in the paraxial regime, we will use paraxial approximation, and therefore, we can write sin theta 1 as theta 1 and sin theta 2 as theta 2. Therefore, under paraxial approximation, the Snell's law reduces to n1 theta 1 is approximately equal to n2 theta 2. Now, from the figure, we can see that theta 1 is equal to phi 1 plus alpha 1. Where phi 1 and alpha 1 are angle measured from the horizontal. Okay. Phi 1 represents the inclination of the perpendicular from the horizontal, while alpha 1 represents the inclination of the incident ray from the horizontal. Similarly, we see that the ray after refraction is inclined at angle alpha 2 from the horizontal. Okay, using this we can write theta 1 is equal to phi 1 plus alpha 1, while theta 2 is equal to phi 1 plus alpha 2. Now, since we are in the paraxial regime, phi 1 is small, and therefore, from the figure we can write phi 1 is equal to, which is here, x by r, where x and r are height of point P and the radius of curvature of the spherical surface respectively. Okay, once these are known, then from equation 6 and 7, what we can write is that n1 phi 1 plus alpha 1 is approximately equal to n2 phi 1 plus alpha 2, where what we did is that we substituted for theta 1 and theta 2 from equation 7 into equation 6, and thus we get equation number 8. Yeah. Now, if we expand this, then we will get n2 alpha 2 is approximately equal to n1 alpha 1 minus n2 minus n1 x by r. Okay. And we also we know that n into alpha is nothing but direction cosine. Okay. Therefore, we can replace n2 alpha 2 by lambda 2 and n1 alpha 1 by lambda 1, where lambda 1 and lambda 2 are direction cosines of the point P, this direction cosines which are lambda 1 and lambda 2, they respectively represents the direction cosine of the ray before refraction and after refraction, right before refraction and right after refraction. And we introduce a new parameter p, which is expressed as n2 minus n1 by r and is defined as the power of the refracting surface. Okay. Do not confuse this p with this point p. These are two different entities. Yeah, these are two different. This point p is point, while this p is a parameter which is defined as n2 minus n1 by capital R, and this represents the power. This represents the power of the refracting surface. Okay. Now, since the height of the ray at point P before and after refraction is the same, what does it mean is the following: the ray from point A, it goes to point P, and then as soon as it falls on P, it get refracted and then it goes towards point B. Yeah. Then right before refraction and right after refraction, this height x is fixed. Yeah. Therefore, what we can write is that x2 is equal to x1. What are x2 and x1? x2 and x1 represents the height of the ray from the axis right after refraction and right before refraction. Since refraction is happening at point P, therefore, x2 and x1 would be equal, because height of the point P is fixed, okay, which is equal to x. Okay. Therefore, we may write equation 10 and 11 in the matrix form. We have two equation number 10 and 11. On the left hand side of 10 and 11, we have lambda 2 and x2 respectively, while on the right hand side we have lambda 1 x1 and p and x here. Yeah, we can write, we should replace x with x1 here for congruence. Yeah, assume that this x is, since x is equal to x2, and this we may assume that is equal to x, because there is only one distance here involved. The height is, there is a single height involved. Height of point P is x. Before refraction we are calling it as x1, and after refraction we are calling it as x2, and both x1 and x2 are the same and they both are equal to x. Yeah. Therefore, using equation 10 and 11, we can write this matrix. Yeah, we can represent these two equations in a single matrix form, which is given by equation number 12, where x1 is equal to x2 is equal to x. Yeah. Now, when we write equation 10 and 11 in matrix form, then what we see is that after refraction, the coordinates of point P after refraction is related with the coordinates of point P right before refraction. Okay, and this relation is expressed by equation number 12. Now, this matrix, which is a 2 by 2 matrix, is called refraction matrix. Okay, always remember this P is the power of refracting surface. Yeah, whenever it is coming in the form of matrix, it is power of refracting surface. Thus, we have a matrix for refraction, which is called refraction matrix. We have already derived an expression for translation matrix, which is given by 1 0 1 d by n. Yeah, this we have derived in our previous class, and in this expression, capital D is the distance between 2 points, and a ray is traveling between these 2 points, and n is the refractive index of the medium. Okay. Therefore, we have a matrix for translation as well as for refraction. This matrix is called translation matrix, while this second matrix is called refraction matrix. It represents refraction. Okay. Note here again that if you take determinant of equation number 13, which is your refraction matrix, it is again equal to 1. Okay. Similar to that of the translation matrix, the determinant of refraction matrix is also equal to 1. Okay. Now, in general, suppose we have a complex system which consists of several lenses. then if you want to calculate the matrix for whole system, then you will have to first calculate the matrix for translation, and if there is refraction, then you have to just put the matrix for refraction, and then again if there is some refraction, then again put the matrix of refraction, and so on, and then you multiply all these matrices, then you will get a resultant matrix, which will again be a 2 by 2 matrix and whose determinant again be equal to 1. Okay. And such a matrix is called system matrix. Okay. And therefore, in general this 2 by 2 matrix is known as system matrix, and it is determined solely by optical system. Okay. Nothing extra is involved. Refraction and translation matrices give rise to system matrix. Okay. Now, since only two operations a ray undergoes in travelling through a transparent optical system, okay, and what are these two operations? These operations are refraction and transmission. I repeat, since only two operations a ray undergoes in traversing through transparent optical systems are refraction and transmission, the ray matrix is in general a product of refraction and translation matrices. Suppose we have a number of optical components which are kept in some order, and you launch a ray, then here it will go through multiple refraction. Okay. Now, what you see here is that this is your translation, and then here refraction happens, and then within the lens again a translation, then here again refraction, then again translation, refraction, translation, refraction, and so on and so forth. For each refraction and translation, we can write a matrix. For translation, we will write translation matrix. For refraction, we will write refraction matrix and multiply them all. And the resultant matrix, which is called system matrix, will have all the informations, which all the informations of the phenomena which happen in this region. Yeah, all this translation and refraction information would be embedded in the system matrix, which is a 2 by 2 matrix. Okay. We will see, we will implement this and will understand how does it work. Okay. Now, as an example, first consider imaging by a refractive surface. Okay. This we have already done. We have calculated, we have seen how a refracting surface refract and how it governs the refraction, and how to calculate focal length in case of a refracting surface or two refracting surfaces. But here in this case, we will implement a matrix method for a very simple case of a single refracting surface. Okay. Now, this curve represent the refracting surface. This refracting surface divides two media of refractive index N1 and N2. Okay. Now, suppose there is a point O from where a ray starts and it falls on a point on a refracting surface, and then after refraction it goes towards point I. The coordinates of point O are, suppose, lambda 1 x1, and then there is another point whose coordinates are lambda prime x prime, and suppose this point is represented by A prime, and this A prime is on the surface of this curved sphere, and it is situated such that on reaching to point A prime, the ray only undergoes translation, and from A prime to A double prime, rays undergo refraction, and the coordinate of A double prime is lambda double prime x double prime. Okay. After emerging at point A double prime, the ray undergoes through a pure translation, and through translation it reaches to point I, whose coordinates are lambda 2 x2. Okay. I repeat, lambda 1 x1, lambda prime x prime, lambda double prime x double prime and lambda 2 x2 are coordinates of O, A prime, A double prime and I points respectively. Okay. Point O is at a distance minus u from P, okay, and point I, the image point, is at a distance v from P. Okay. P is the point on the axis of this refracting surface, the curved refracting surface. Since u is on the left hand side of P, then using our sign convention, we can say that u would be a negative quantity, a negative number, while v, which is on the right hand side of P, it would be a positive number. Okay. Knowing all this, we will write a matrix for this translation, refraction and translation again, and we will see how does the resultant system matrix looks like. Okay. Now, for translation of the ray from point O to A prime, what are point O and A prime? Point O is here and A prime is here. Now, for this distance O A prime, which is a pure translation, we will write as matrix, which would be a translation matrix. Now, lambda prime and x prime are the coordinates of point A prime and lambda 1 x1 are the coordinates of point O. Okay. Now, these two would be related through this matrix. Okay. And what is this matrix? This is your translation matrix. Okay. Okay. And we have already derived the equation to connect lambda 1 x1 and lambda prime x prime in our previous class. Therefore, equation 14 represents this connection, and these coordinates of O and A prime are related with a translation matrix. Okay. We know that the translation matrix has this formula 1 0 d by n and 1 d is the separation horizontal separation between the points within which the ray is traveling. Okay. And since the distance here between O and A prime is minus u, therefore, we will replace d with minus u, and therefore, instead of d by n, we have minus u by n1, where n1 is the refractive index of the medium. As stated before, on the left hand side of this refractive index, on the left hand side of this curved surface, the refractive index of the medium is n1. Okay. Therefore, we replaced n in the denominator by n1. Okay. Therefore, d by n is written as u by n1. Okay. And this is this element here. Okay. Similarly, the coordinates of A double prime and A prime can also be related, and since here it is refraction happening, we will use refraction matrix. Yeah, I repeat, the ray starts from O and it goes to A prime. There is only translation involved. From A prime to A double prime, it is refraction, and from A double prime to I, it is again only translation. Therefore, for O to A prime, we will write translation matrix. From A prime to double A prime, we will write refraction matrix, and from A double prime to I, we will again write translation matrix. Now, for the second case, means for refraction, we will relate double prime, lambda double prime and x double prime with lambda prime x prime with a refraction matrix. This is your refraction matrix. Okay. And here P is your power of the refracting surface, element P is power of the refracting surface. Okay. And at last, for the translation from A double prime to I, we can again write this translation matrix. Here the D is replaced by V, while N is replaced by N2, where N2 is the refractive index of the medium, which is on the right hand side of the refracting surface. Okay. Therefore, we have this type of translation matrix. Now, we have represented all the translations and refraction in matrix form. What is our ultimate goal? We want to relate lambda double prime x double prime with lambda prime x prime. How to do this? We will substitute lambda prime x prime from equation number 14 to equation number 15, and this will give the expression for lambda double prime x double prime, and then the final expression of lambda double prime and x double prime would be substituted to equation number 16. This will give a relation between lambda 2 x2 and lambda 1 x1, and which is given by equation number 17 here. This relates lambda 1 x1 with lambda 2 x2, okay, in matrix form. Note the order of the matrices. Okay. This is your translation matrix, this is your refraction matrix, and this is your again translation matrix. This is your first translation, this T is first translation. Okay. Therefore, let us write it as T1 and this would be your T2. This is for the second translation. Okay. What are first and second translation? This is your first translation, then refraction here, and this is your second translation. The same things are represented here in the matrix form. We have your coordinate of point 2 as lambda 1 x1, then it is operated with translation matrix, and then the resultant with reflection matrix, and then finally with the again second translation matrix. This give you the resultant expression. Now, after all this multiplication here, the two translation and one refraction matrices are multiplied, and ultimately you get this 2 by 2 matrix. This is your system matrix. Okay. Now, system matrix relates the coordinates at point O with the coordinates at point I, the image point. Now, we will expand equation number 18 for the expression of x2. Now, if you expand 18 for expression of x2, then we will get this. Okay. Now, suppose our object is a point object which is situated on the axis of the system. If this is the case, then x1 would be 0, because x1 is the height of the object from the horizontal axis, from the axis of the system, and if it is a point object situated on the axis, then this height would be 0. Therefore, x1 would be 0. Okay. And if our object is a point object which is on the axis of the system, and this will lead to a point image. Okay. And since the image is a point image, therefore, x2 would again be equal to 0. Now, once x1 and x2 are 0, which is for axial point object and point image, then from equation 19 we will get that this term, the first term on the right hand side, should be equal to 0, but lambda 1 cannot be equal to 0. Therefore, the coefficient associated with lambda 1 must be equal to 0, and therefore, we will equate this term in the bracket to 0. Now, if you equate this term to 0, then we will get this relation, which is equation number 20. Okay. For axial objects, axial point object and axial point image, we will get equation number 20. Okay. And once this is given from equation 20, we can, after some mathematics, we can calculate or we can get an expression of P, which is power of our refracting surface. Okay. But we know that P is equal to N2 minus N1 by R, capital R, where N1 and N2 are refractive indices of the medium 1 and medium 2, the medium which is on the right hand side of the refracting surface and the medium on the left hand side of the refracting surface. Okay. N1 is a medium which is on the left hand side of the refracting surface, and N2 is the refractive index of the medium which is on the right hand side of the refracting surface, and R is the radius of curvature of the this refracting surface or curved surface. Okay. We will substitute this expression of P into expression 22, and this will give equation number 23, yeah, which is N2 by V minus N1 by U is equal to N2 minus N1 by capital R, which is nothing but law of refraction from a curved surface which we have already derived. Yeah, N2 by V minus N1 by U is equal to N2 minus N1 by R, which is a relation which we derived in our previous classes for a curved refracting surface, which we just implemented Snell's law, and from there we derived this relation. Okay. Let us go back again. What we did, we substituted this term equation. What does equation number 20 represent? Equation number 20 represent this term of the matrix. Okay. This is nothing but your equation number 20. Okay. We equated this term of the matrix to 0, and this constitute equation number 20, and this gives a valid relation which we derived earlier. Therefore, this term of the matrix would be 0. Okay. Once you substitute it to 0 from this equation number 18, we can write this relation. Okay. Here this term is replaced with 0. Okay. And now again we will expand equation number 24 for expression of x2, then we will get equation number 25. x1 and x2 are height of the object and height of the image. Okay. Now the ratio x2 to x1 is nothing but magnification, which we have already defined. Okay, in our earlier classes we defined magnification as the height of the image upon height of the object, and here what is x2? x2 is the height of the object, x1 is the height of the image, and from equation 25 we can find this ratio, and which is equal to 1 minus V P by N2, where P is again power of the refracting surface. Okay. Now using equation 23, we can simplify equation 26. What is equation 23? This. Okay. Now we will apply 23 into 26, or we will substitute for the expression of P, which is nothing but N2 minus N1 by capital R, and then we will get this expression for magnification. Okay. This is how we can treat refraction from a curved surface using matrix method. Okay. We started with point O, and then we calculated the magnification. Okay. And then we calculated also the system matrix. These informations we derived very easily without resorting to the Snell's law. Okay. We will again take another example and this example is of coaxial optical system. Okay. Optical system means instead of having a single refracting surface or some translation, we have suppose a black box with any number of lenses, and these lenses are different kinds. Few are concave, few are concave. Multiple varieties of lenses are kept coaxially in a box, and the upper surface of the box is refracting surfaces, which are given by these two curves, this left and right curves, which binds these optical system. Yeah, the optical system is within this left and right curves, and we do not know what is there inside it. It is like a black box. Then now here we will see what help we can get out of the matrix method. Okay. What are the given quantities here? Okay. there is an object O which is situated here, okay, and this object O is at a distance d1 from the left refracting surface of the optical system. This is the left refracting surface of the optical system, this is the right refracting surface of the optical system, and suppose the radius of curvature of the left refracting surface is represented by R1 and the radius of curvature of the right refracting surface is represented by R2. Okay. D1 is the position of the object from the left refracting surface and D2 is the position of the image from the right refracting surface. Okay. Now, OO prime is the height of the object, which is x1, and the coordinate of O prime is lambda 1 x1, okay, and from O prime a ray emanates and it falls on the left refracting surface of the optical system, and the coordinate of this point is x lambda prime x prime. Similarly, the ray, we do not know what is happening inside this black box, no information is given, okay, but the ray emanates from point Q here, okay, and the coordinate of point Q is lambda double prime x double prime, and then the point comes at image point I prime whose coordinates are lambda to x2, okay, and the refractive index on the medium on the left hand side of the optical system is n1, while the refractive index of the medium on the right hand side of the optical system is n2. Okay. These informations are given. Now, what to do? Now, we see that from O prime the ray is travelling, it is translating to point P. Okay. Then here we will apply a translation. Now, again after emerging from this optical system, the ray is again translating from Q to I prime. Okay, these two translations are known, but within this box what is happening nobody knows, and therefore, we cannot form a matrix, we cannot form a 2 by 2 matrix for this system. Okay. So, let us see how to analyze this. Okay, for the first translation which is happening in the first medium of refractive index n1, we can write this equation which is again in matrix form, and this is your translation matrix, the first translation. Okay, the refractive index on the left side is n1 and distance is d1, therefore, d by n would be replaced by minus d1 by n1. And minus sign is there because the object is on the left hand side of the refracting surface. Okay. In the black box in this optical system where no information is given, let us relate the 2 points. What are those 2 points? Point P and point Q, and the coordinates of these 2 points are related with a matrix, again 2 by 2 matrix, but since its elements are not known, we assume these the elements of this matrix as A11, A12, A21 and A22. Okay. Now, for the third case, which is again translation from Q to I prime, we can again write this matrix equation, where the second translation matrix, this T, can be written very easily, where d2 by n2 is nothing but it is a distance, d2 is the distance of the image from the right refracting surface, and n2 is the refractive index of the medium which is on the right side of the optical system. Okay, if we know this, then we will combine to equation 28, 29, 30 as we did previously. How to combine this? This would be substituted here in equation number 29, and once the expression for lambda double prime x double prime is known, this would be substituted here in equation 30. This will ultimately relate lambda to x2 with lambda 1 x1 with this complex matrix, 2 by 2 complex matrix, which is given by expression 31. And what are unknowns here? Unknowns are A11, A12, A21 and A22. Okay, let us proceed further. As a boundary condition, we will again use this. Suppose the object is a point object and image is also a point image, and they both are axially situated. They are axial point object and axial point image. If this is the case, then x1 and x2 would be equal to 0. yeah, both x1 and x2 would be equal to 0. And if you substitute so and expand equation number 31 for x2, the expression of x2 as we did previously, then the coefficient of lambda 1, this will be the coefficient of lambda 1 and this must be equal to 0. Okay, we are just repeating this step which we did previously here. Okay, we are having equation number 18, then we expanded 18 to get an expression for x2, and this term, the coefficient of lambda 1 must be equal to 0. Okay, and the same thing is being repeated here. This is the coefficient of lambda 1 which we now have equated to 0, which is our equation number 32. Then the equation 31, which is our master equation here, this term would be equal to 0. Since it is all equated to 0, we will get equation number 32. Okay, here this term is 0 now. We will again expand equation 32 to get an expression of x2, and this will lead to equation number 34. Okay. Now, let us again calculate as we did previously. Let us again try to find the expression for magnification, which is equal to x2 by x1, the height of image to the height of object. Okay. This ratio is magnification. Now, from equation 34, if you calculate x2 by x1, then you get this expression, which is a22 plus a12 into d2 by n2. This is the expression for magnification. Okay. Once we know what magnification is now, yeah, which is a22 plus a12 into d2 by n2, and there is one more condition on this matrix. This is our matrix. Okay. This is our matrix, on this matrix, which is a system matrix. The second condition is that its determinant must be equal to unity. Yeah. Now, let us exercise this second condition, which is the determinant of the system matrix must be equal to unity. Then what we get is the following: we obtain this expression is equal to 1 by this expression. Okay, this is what it is written here, but this term is equal to magnification. Therefore, we can write 1 by a22 plus a12 d2 by n2 is equal to 1 by m. M is nothing but your magnification. Okay. It means the first term of the matrix is equal to magnification, and inverse of the second term, sorry, the first term is equal to inverse of magnification, and the fourth term is equal to magnification, and therefore, the resultant form of the system matrix would be something like this. Okay. This is the final form of the resultant matrix. Okay. Now, conclusively, we started with a system matrix where there were so many unknown terms which were a11, a12, a21, a22. Now, after analyzing the system using matrix method, we found a simplified matrix whose first term is inverse of magnification, last term is magnification, this term is equal to 0, only unknown is this term a12. A12 is only unknown we are left with. Okay. Now, in we will see, like in we will study a few more topic and see what a12 represents, but for now we know that if a very complex optical system is given, then we can form its system matrix. Okay. When can we form its system matrix? Before the if we know what is the position of object, what is the height of the object, and if we know what is the position of the image and what is the height of the image, then with this information we can find 3 element of the 2 by 2 system matrix. Only one unknown is left. Okay. This is the beauty of the matrix method, and for this unknown we will do further analysis and we will see what happens. Okay. And this is all for today. We will talk more about the implementation of the matrix method in the next class.